Okay, so I'm going to post this question online as well, just in case you can't read it here, because it is pretty zoomed out. And I'll read it here in a second. This is WebWork Homework 4, number 17. The question reads, a person leaps from an airplane 6,500 feet above the ground and deploys his parachute after 3 seconds. Assume that the air resistance both before and after deployment of the parachute results in a deceleration proportional to the person's velocity, but with a different constant of proportionality. Before deployment, take the constant to be 0.15, and after deployment, use the value 1.6. The acceleration due to gravity is 32.2 feet per second squared. Note also that the constants of proportionality given are rho equals k over m, not k. Part A reads, how fast is the person going when the parachute is deployed? So the first thing we're going to do is we're going to think about the forces acting on the person. So if this is a force body diagram, then the forces acting down on the person is equal to mass times gravity, and the force acting up on the person is equal to this constant of proportionality times the velocity. We're just going to write this down just to remember it. Before he opens the parachute, the constant of proportionality, k over m, is equal to 0.15, and after, k over m is equal to 1.6. So let's write a sum of the forces equation. The sum of the forces on the person is equal to mass times acceleration, as we know, F equals ma, which is equal to, in this case, mg minus kv. Now we're going to solve for the acceleration because we can use this, since we know that a is equal to dv dt, to solve for v. So the acceleration is equal to mg minus kv over m, which, when simplified, is equal to g minus k over m times v. Since we know that this is equal to dv dt, we can use the separation of variables technique on this differential equation to write that 1 over g minus k over m times v dv is equal to t dt. And we're going to integrate both sides of this equation. So when you integrate this, this is going to be the constant term that is multiplies the natural log. So it's going to be 1 over this. So it's going to be negative m over k ln natural log absolute value of g minus k over m v is equal to t plus c, which is going to be the constant of integration. So now we can use this equation to solve for v, because we've integrated both sides. So we can multiply this over here so that it is natural log of g minus k over m times v is equal to k over m, negative k over mt, and technically we could write k over m times c, but it's easier just to keep it as c because we know it's just a different constant. So these are two different constants, but it doesn't really make a difference because we don't have a value or an equation for that constant yet anyways. So now we're going to make both sides base e so that we can get rid of this natural log. So we can get rid of it, so it'll be natural log of g minus k over mv is equal to e to the negative k over mt. And then since this is plus c, it's the same as saying e to this times e to the c, and e to the c is another constant, so we can move this out front to be a new constant. So this is also a different c. Okay, So now, because of the absolute value signs, we know that this can be plus minus. And I'm also going to do 2 steps right now and say that, or actually, no, I'll just write the one. So it's G minus K over MV equals plus minus CE to the negative K over MT. Awesome. Okay. So let's go up here, I guess. So now that we have this, we know that we can simplify this more by moving this to the other side to make the term with V in it be positive. So I'm just going to keep it on this side, but I'm adding it to the other side. And then I am moving this to this side. I'm just flipping it so that it's easier to read. So it will be G, and in this case we want C to be or we want this term to be negative. So it's going to be negative CE to the negative K over MT. We want this to be negative because the net force is down. So now that we have that, and we can multiply this over so that it is V equals M over K times G minus CE to the negative K over MT. So now what we can do is we can take out this G because this is a constant. So if we divide a constant by another constant, it's still a new constant. So we can do V is equal to G M over K times 1 minus a different constant, E to the negative K over MT. So now we can find the value of C because we know that at time 0, the person hasn't jumped yet, and so his velocity is 0. So we can solve this by saying 0 equals, so this is a constant, but I will rewrite it here, 1 minus C e to the 0. So this obviously goes to 1, and we need this term to be 0 so that this entire side of the equation can be 0. The only way that can happen is if C is equal to this term here, so that means C is equal to 1. So now we have a full equation for the velocity of the person. So the equation is V equals Gm over K times 1 minus E to the negative K over MT. So this is the velocity. We can simplify this by plugging in the constants, and then we're going to plug in the time at which the parachute is deployed, which is 3 seconds, so that we can get the speed at that time. So we're finding V at 3 right now. We know that G is equal to 32.2 feet per second squared. M over K is just the reciprocal of K over M, so that's times M over K is the same as divided by K over M, which is 0.15. Then it's 1 minus E to the negative K over M, which is 0.15, and T we know is 3. So if we plug that into our calculator, which I'm going to do right here, so that is the constant. Oh, I forgot one of my parentheses. There we go. Minus E to the negative 0.15 times 3. We get 77.79 feet per second. So this is the speed that the person was going when the parachute was deployed. That's the answer to part A. Now we're going to move on and find the answer to part B. When we need this work later, then we can come back and look at it, but right now I'm going to take it off the screen. So part B is, how high off the ground is the person when the parachute is deployed? Okay, so for this part, we need to be aware of the fact that distance is the integral of velocity. So we are going to integrate the equation that we found in the last part. So we found that v is equal to gm over k times 1 minus e to the negative k over mt. Okay, so we know that the integral of velocity is equal to distance, which we're going to represent with an s here. So we're going to say s is equal to the integral of velocity, which is equal to the integral of gm over k, 1 minus e to the negative k over m times t. Awesome. So to integrate this number, we are going to, first I'm going to expand this because I think it will be easier if we don't have a constant on the outside. So I'm going to say that s is equal to the integral of gm over k minus gm over k e to the negative k over mt. And then we are going to integrate this with respect to t, which I actually forgot my dt's. I will add those now. So this is a constant, so when we integrate that, it's just going to be gm over k times t, how we would integrate any constant. And then the integral of e to the kt is, so we're going to bring the reciprocal of this exponent out to the front because we want to multiply it so that we have the correct constant there. So since this is negative and this is negative, this is going to be positive. We're going to multiply m over k, which is the reciprocal of this, times the current constant, which is gm over k, and then this is going to stay the same because it's e. Awesome. Okay, and we also need a plus c because there's always a constant of integration. Okay, so let's find c. So we know that the distance at time 0 is equal to 0 feet. He hasn't fallen anything yet. That's when he first jumps out of the plane. So he hasn't moved yet. So we're going to plug in 0 for both t and s. So we're going to say 0 is equal to gm over k t. Or, whoops, 0. That's a 0. Plus, and I can simplify this by saying gm squared over k squared, e to the negative k over m times 0 plus c. So this, again, goes to 1 because anything to the 0th power is 1. This goes to 0. So we're left with 0 is equal to gm squared over k squared plus c, which means that c is equal to negative gm squared over k squared. So now we have a full equation for distance, which is equal to s equals gm over k t plus gm squared over k squared e to the negative k over m t minus gm squared over k squared. So this is our distance equation here, and we're going to use this. We need to find how high off the ground the person is when the parachute is deployed. So we know that this is at t equals 3, but this equation doesn't give us height off the ground. This equation gives us distance fallen. So our final answer is going to be 6,500 minus our answer of s of 3, because that's going to be equal to the distance, the total distance minus the distance fallen, which gives us the height. So now we're going to plug in all of our values into here. I'm not going to bore you with all of the math. You know what all the constants are based on part A, based on the question. But when you plug in 3 for t, what you get is, and I have it up here, I believe. There we go. You get s of 3 equals 125.41. Or is approximately. That's not, obviously that's not the exact answer, but it's close enough for this problem. So now we're going to take 6,500 feet, subtract 125.41, and as you see, I previously calculated up here, the answer is equal to 6374.59, and that's in feet. So this is our answer to part B. I'm going to move this off the screen now. So the next part of the problem is when we find approximately to 1 decimal place, how much longer does it take the person to reach the ground? In seconds. So for this part of the question, what we need to do is we need to take our velocity equation that we found in part A, v equals gm over k times 1 minus e to the negative k over mt. And we actually need to put back the constant of integration right there, because our constant of proportionality has changed, and so has our initial velocity. So we're going to find that constant again. So now, since the constant, basically what I'm doing is I'm rewriting this to say that the velocity at time 0 is equal to the velocity when the parachute is deployed. So basically I'm starting this when the constant of proportionality changes. So what I know is that v at time 0 now is equal to 77.79 feet per second. So now that I know that, based on our answer to part A, what I'm going to do is plug in 0 and this value to find a new value for c. So when you do that, you get our new c is equal to negative 2.87. So now we have a new velocity equation for when the constant of proportionality is 1.6. Remember that when you're solving for this c value, the k over m value is no longer 0.15, now it is 1.6, and you get the c. So now we have a new velocity. And we are going to integrate this velocity. So v equals gm over k times 1 plus 2.87 e to the negative k over mt. We're going to integrate this the same way we integrated the velocity in the last part to give us a distance equation. So we can do that. We can say that s is equal to the integral of v dt, which is equal to the integral of gm over k plus 2.87 gm over k e to the negative k over mt. This is all part of the integral. And then once we integrate this, what we're going to do is we're going to plug our distance. So this is going to be our answer from part B, because that's the distance left to fall, 6374.59, and it wants how much longer it takes the person to reach the ground. So we're starting here, and we're going to 0. So this is the distance that the person needs to fall, is equal to the integral of this, where t is what we're looking for. So we're going to say gm over kt plus 2.87 times, as you remember from last time, gm squared over k squared e to the negative k over mt. So this is our new equation. You can plug this into your calculator to get t. T is the only variable that we still have. You can plug this into the equation. You can move this into the other side if you'd like, and find when the full equation. So I'm going to write this out just to make it clear. We can do 32.2 times 1 over 1.6. So I'm just going to divide by 1.6 t plus 2.87 times 32.2, and again it's m over k, so that's divided by 1.6 squared e to the negative 1.6 t. So now that we have a full equation, you can move 6374.59 to the other side. So now we have 0 equals. You can plug this equation into your calculator, which I guess I will do for you now, just so that you can see what I'm doing. 32.2 divided by 1.6 times x, or in our case t, but times 2.87 times 32.2 divided by 1.6 squared times e to the negative 1.6 x minus 6374.59. So when we graph this, so we need to find the value when y is equal to 0, so we're going to actually expand this window a whole lot because we know that it's far away. Or I guess I know, you could do some experimentation and figure it out. So now what we're going to do is we're going to calculate the 0. So left bound right bound, as you see, we passed it, there we go. You can press enter again, and it gives you a value of t equals 316.75. So it just wants one decimal place. So we can just say 316.8 seconds. And that's the answer to part C. Okay, so that is all of web work, homework for number 17, parts A, B, and C. The question should be posted along with this video on Blackboard. Thank you for watching.